So now let's discuss about Euclid's division lemma. Euclid's division lemma. Yes. So as the name suggests, this Euclid's division lemma has to do with the divisibility of numbers. Okay. So now what do you mean by lemma? Lemma means a proven statement. Lemma means a proven statement that is used for proving some other statements. Yes, is it clear? Lemma means actually it's a proven statement. It is some proven statement that is used for proving some other statements. Okay. Now, what do you mean by Euclid's division lemma? Okay. So Euclid's division lemma simply states that any number, any positive integer a can be divided by another positive integer. Any positive integer a can be divided by another positive integer b where a is greater than b, producing a unique quotient and remainder, where remainder can either be 0 or a value greater than 0 but less than b. Yes. So Euclid's division lemma states that any positive integer can be divided by another positive integer. Yes, and it produces, when we divide a positive integer by another positive integer, yes, it produces a unique quotient, and a remainder, and the remainder value can either be 0 or a value greater than 0 but less than the divisor value. Okay. So now let's try to understand this. With the help of an example. So let's take two numbers, 99 and 7. So let's take two numbers, 99 and 7. Okay. Here, yes, we know 99 is greater than 7. So here we know 99 is greater than 7. And here we are going to divide 99 by 7. Okay. So we know the number that we are dividing. Is known as dividend. And the number by which we are dividing is known as divisor. So in this example 99 is the dividend and 7 is the divisor. Okay. So now let's divide 99 by 7. Yes. So first we have to find how many times 7 goes into 9. So into 9 7 goes only one time. So 1 7 is 7, remainder 2, 29. So now we have to find how many times 7 goes into 29. So into 29 7 goes 4 times. So 4 7s are 28, remainder 1. Is it clear? So when we divide the number 99 by 7, yes, it produces a quotient 14. And the remainder value is 1. Is it clear, guys? So here we can see 1 is less than 7. Okay. Suppose I am dividing a number 104. Okay. 104 by 7, again by 7. So here in this example 104 is the dividend and 7 is the divisor. So first we have to find, how many times 7 goes into 10. Usual division process. Okay, here we are performing the usual division process. Yes, okay. So first, how many times 7 goes into 10? 7 goes into 10 by one time. Only one time. So 10 minus 7 is equal to 3, 34. Now how many times? So now how many times 7 goes into 34? 4 times, isn't it? Yes, 4 times. So remaining the number is 28 and the remainder is equal to 6. Here also you can see. So here also you can see 6 is a value that is less than that of 7. 6 is a value that is less than that of 7. So let's take another example. Suppose I am dividing. Suppose I am going to divide 105 by 7. Okay. So here again, how many times 7 goes into 10? Only one time. So 7, 3, 35. How many times? 5 times. So 35 and remainder is equal to 0. Here the remainder value is equal to 0. Again, let me take another number. Say for example 106. So if I take the example if I divide 106 by 7, again one time 7, 3, 36, 5 times. So again 35, remainder 1. Suppose I take here 8, 108. Suppose I am dividing 108 by 7. Then the remainder obtained, will be is equal to 3. If you divide, so yes, here we divided 4 different numbers. Here we divided 4 different numbers by 7, and you can see the value of the remainder, are either 0. The value of, or we can say remainder is equal to 0 or a number greater than 0 but less than that of 7, isn't it? Let's take one more example. If we are dividing 77 by 7. So how many times 7 goes into 77? 11 times. So 7, the remainder is 0. So when we divide any number, you can take any random number. Okay, you can take any random number and you divide the number by 7. Yes, the remainder value obtained will always be either 0 or a value greater than 0 but less than 7. Is it clear, guys? That is what our Euclid's division lemma states. Euclid's division lemma states when a positive integer is divided by another positive integer. When a positive integer is divided by another positive integer. Okay, where the dividend is greater than divisor, it produces a unique quotient and remainder, and the remainder value will always be either equal to 0 or a value greater than 0 but less than the divisor. Is it clear, guys? Yes. So we know the number that we are dividing, is known as dividend, and the number by which we are dividing is known as the divisor, and the answer obtained, or yes, the answer to the question how many times. So how many times a particular number goes into another number? Yes, how many times a particular number goes into another number? That will be the quotient. Okay, that will be the quotient. And again the remainder, this one is known as the remainder. Is it clear, guys? This one is known as the remainder. Is it clear? Okay. Here in all of these examples, yes, you can see, that is, let's consider this one. So we can see 14 into 7 plus 1. 14 is the divisor, isn't it? 14 is the divisor. Sorry, not 14, 7 is the divisor. 14 is the quotient and 1 is the remainder. Okay. So when we multiply quotient by divisor and add 1 or add the remainder value to the product, the result obtained is 14 into 7 is 99. The result obtained is 14 into 7 is 98 and plus 1 is 99. Here we can see 99 is our dividend. 99 is our dividend value, isn't it? Yes. Let's take another example. Say for example this one. So here we can see 15 into 7 plus 0 is equal to 105. 15 is the quotient, 7 is the divisor, and 0 is the remainder. Is it clear? Okay, let's take another example. 15 into 7 plus 3 is equal to 108. So we can conclude. That dividend is equal to. So we can conclude that dividend is equal to. So we can conclude that dividend is equal to divisor into quotient. Dividend is equal to divisor into quotient plus remainder. Divisor into quotient plus remainder. And here remainder can either be 0 or a value greater than 0 but less than divisor. But less than divisor. Is it clear? Not equal to divisor or not greater than divisor. The value, the remainder value will be always less than divisor. Is it clear? Yes. Okay. So now we can rewrite this equation. So we can rewrite this equation in terms of A and B. We know here we are dividing A. Here we are dividing A by B. So A is the dividend and B is the divisor. Let the quotient obtained be Q and let the remainder obtained be R. So we can say A is equal to BQ plus R. A is equal to BQ plus R where R less where 0 less than or equal to R less than B and also A greater than B. Is it clear, guys? Yes. This equation or this formula is known as Euclid's division lemma formula. This formula is known as Euclid's division lemma formula. Is it clear, guys? Euclid's division lemma formula. So yes. Okay. And in your textbook it is given like Euclid's division algorithm. Euclid's division algorithm. Yes. So what do you mean by Euclid's division algorithm? Euclid's division algorithm is an algorithm that uses Euclid's division lemma. Euclid's division algorithm is an algorithm that uses Euclid's division lemma for finding the HCF of two numbers. Is it clear, guys? Yes. This Euclid's division algorithm is in this algorithm we use Euclid's division lemma repeatedly until the remainder is 0. Is it clear, guys? Okay. Euclid's division algorithm is actually an algorithm that uses this Euclid's division lemma. That is A is equal to BQ plus R. A is equal to BQ plus R for finding the HCF of two numbers. And this algorithm uses Euclid's division lemma. This algorithm uses Euclid's division lemma repeatedly until the remainder becomes 0. Is it clear? Okay. Yes. So now let's discuss the two major applications of Euclid's division lemma. Yes, as far as your syllabus is concerned, we have to deal with two applications of Euclid's division lemma. The first application is to find the properties. Yes, means, say for example, we have to using this Euclid's division lemma, we have to show that, or we can show that some statements are regarding the properties of numbers are true. Say for example, all the positive even integers are in the form 2q. Yes, this is one statement. This is one statement regarding one of the property of numbers, isn't it? Yes. So we can show this, or we can prove this using this Euclid's division lemma. Is it clear? Okay. Another property, say for example, all the positive odd integers are in the form 2q plus 1. Yes. Or else another property, the square of all the positive integers, are either in the form 3m or in the form 3m plus 1, etc. Yes, these are some statements regarding certain properties of numbers. Yes, we can show that these statements are right. We can show that these given statements are right using Euclid's division lemma. Is it clear, guys? So that is the first application. Of Euclid's division lemma. Okay. Then the second application is to find the highest common factor. HCF means highest common factor and LCM means least common multiple. Okay. So to find the HCF of two numbers. of two numbers, and usually we use Euclid's division lemma. For finding the HCF of two very large numbers. Is it clear, guys? Okay, yes. So these two are the two applications of Euclid's division lemma. Okay, yes. Now in your examinations, you can expect two types of questions. Two types of questions from this section. In your examination, you can expect two types of questions from your examinations, and both of these types are related to the applications of Euclid's division lemma. The first type is related to the first application, that is to find the properties of numbers, and the second type of question is related to the second application, that is to find the HCF of two numbers. Is it clear, guys? Yes. So let's deal with the first type of question. Okay, yes. So I told you the first type of question is related to the first application of Euclid's division lemma. Okay. So first type question, let me write one question. Okay. So show that all the positive even integers are in the form 2q, and all the positive odd integers are in the form 2q plus 1. Okay. Yes. So this is a type 1 question. So in such questions, in type 1 questions, you will be provided or you will be given a statement. And you will be asked to prove that, or you will be asked to show that the given statement is true. Is it clear? Using Euclid's division lemma. Is it clear? Sometimes they may specify. Like using Euclid's division lemma. Sometimes it will not be there. Sometimes yes, it will not be specified. But you have to understand that if you happen to see this type of questions, yes, you have to show this, or you have to prove this using Euclid's division lemma. Is it clear? Okay. Where q is some whole number. Yes. Okay. So where q is some whole number means, yes, the value of q can be 0, or the value of q can be 1, 2, 3, 4. It goes on forever. Is it clear? Okay. Now let's see how do we Now let's see how to prove. Now let's see how to prove the given statement is right. Yes, as I told you, for proving this, yes, we have to use Euclid's division lemma formula. So we all know A is equal to BQ plus R. A is equal to BQ plus R, where R 0 less than or equal to R less than B. Okay, yes. So the first four steps of all the questions of this type, the first four steps of all the questions of this type is one and the same. Okay, so let's start. So the first step, so step 1. So step 1 is to assign a value. Step 1 is to assign not a value, assign a variable to A. Assign a variable to A. Okay. So the first step is to we have to assign a variable to A. Let A is equal to X. So we can say X is the positive integer. So X is the positive integer that we are dividing. Okay. So we can say X is the dividend. So we can say X is the dividend. Is it clear? Okay. Now let's see the second step. Yes. So when we perform the mathematical operation division, we know we need two numbers, isn't it? One number will be the dividend, and the other number will be the divisor. Okay. Now we have our dividend. Now actually after the first step, we have our dividend. But now we don't have our divisor, isn't it? So the second step is to find the divisor value. Okay. So what is the divisor value? So what is the value of divisor? How do we find that? So for finding the divisor value, or the value for finding the divisor, yes, we have to. For finding the divisor, yes, we need the expressions. For finding the divisor, we need the expressions given in your statement. Okay. So always the expression given in your statement, will be in the form coefficient into variable plus constant. The expressions given in the statement will always be in the form coefficient into variable plus constant. Is it clear? Okay. And you should choose the coefficient of the variable. As the divisor value. Is it clear, guys? Say for example, if suppose it is given 3m plus 9. If suppose the given expression is in the form 3, the given expression is 3m plus 9. Okay. So this is the coefficient and this is the variable and this is the constant value, isn't it? So you have to choose this coefficient 3. As the divisor. Is it clear? Let's take one more example. Suppose it is given 8t. Suppose it is given the given expression. Suppose the given expression is 8t. Okay. So here in this form, there are two terms, that is coefficient into variable plus constant. But here in this expression, there is only one term. If sometimes the given expressions may contain only one term. In such cases you can rewrite the expression as plus 0, that is 80 plus 0. Yes. Now you can compare these two equations. Now you can compare these two expressions, that is, this is the coefficient, and this is the variable, and this is the constant value. Is it clear? So now you can choose this 8. You can choose this 8, coefficient 8 as the divisor. Is it clear? So always you have to choose the coefficient of the variable. Coefficient of the variable in the given expression as the divisor. Is it clear? Okay. Now back to our question. In our question, two expressions are given. So the first expression is 2q, and the second expression is 2q plus 1. Yes, we can rewrite this 2q as 2q plus 0. We can rewrite this 2q as 2q plus 0, isn't it? So both of these expressions are in the form coefficient into variable plus quotient. Not quotient, constant, isn't it? Yes. So in the first expression, 2 is the coefficient, q is the variable, and 0 is the constant. And in the second expression, q is the variable, 2 is the coefficient, and 1 is the constant. I told you, you have to choose the coefficient of the variable in the expressions given as the divisor. So here the coefficient of the variable is 2. So we have to choose 2 as the divisor. Is it clear? So we have to choose 2 as the divisor. Okay. So now we got dividend and divisor. So step 3 is to rewrite the equation, or step 3 is to rewrite, or we can say step 3 is to substitute. Step 3 is to substitute the dividend and divisor values. For a and b in the Euclid's division lemma formula. Okay. So we know a is equal to x. So x is equal to, we know b is equal to 2. So 2q plus r. Is it clear? So step 3 is to substitute. Step 3 is to substitute the dividend and divisor values. For a and b. In the Euclid's division lemma formula. Is it clear? Yes. And we have done that. X is equal to 2q plus r. Okay. Now step 4. Yes. Now step 4 is to find all the possible forms of x. Step 4 is to find all the possible forms of x. So how do we find all the possible forms of x? It's very, very easy. And for that, for finding all the possible forms of x, that is all the possible forms of positive integer, you have to find all the possible remainder values. Is it clear? So here in this question we are dividing. Here in this case we are dividing the positive integer x by 2. So the possible values of remainder, r can either be equal to 0 or r can be equal to 1, isn't it? Yes, r can either be equal to 0 and else r can be equal to 1. Is it clear? Okay. Now we have to substitute. These 0 and 1. For r. That is, x can either be in the form 2q plus 0, or x can be in the form 2q plus 1. Is it clear, guys? Yes. The fourth step. What is the fourth step? The fourth step is to find all the possible forms of x, all the possible forms of the positive integer x. Okay. So how do you find all the possible forms of x's? And for that, for finding all the possible forms of x, you have to find all the possible values of remainder. Yes. So here in this case, we are dividing the positive integer x by 2. So we know the divisor is the divisor value or the number by which we are dividing the positive integer is 2. So only two remainder values, only two values are possible for the remainder, and they are 0 and 1. That is, the remainder can either be 0 or it can be 1. So there are only two possible forms of x. Yes. So x can either be in the form x is equal to 2q plus 0 or be in the form x is equal to 2q plus 1. Is it clear, guys, up to this? Yes. Okay. Now we all know even numbers are perfectly divisible by 2, isn't it? Even numbers are perfectly divisible by 2. Yes. When a number is perfectly divisible by another number, it leaves a remainder 0. When a number is perfectly divisible by another number, it leaves a remainder 0. Is it clear? Yes. Only even numbers are perfectly divisible by 2. Is it clear? Yes. Only even numbers are perfectly divisible by 2. Is it clear? Okay. Now let's take this possibility, or now let's take this form of x. Okay. Here in this form, the remainder value is equal to 0. Here in this form, the remainder value is equal to 0, isn't it? Yes. Since the remainder is equal to 0, we can conclude, x is perfectly divisible by 2. Is it clear? Yes. Just now I have told you only even numbers are perfectly divisible by 2. So here, yes, since the remainder is 0, since the remainder obtained is 0, x is perfectly divisible by 2. So we can say x is a positive even integer. And the given positive even integer x is in the form 2q. Is it clear? So we can, since x is perfectly divisible by 2. Why x is perfectly divisible by 2? Because the remainder obtained is 0, and we all know only even numbers are perfectly divisible by 2. Yes. So we can conclude x is a positive even integer in the form 2q. Is it clear? So thus we have proved all the positive even integers are in the form 2q. Is it clear, guys? Okay. Now when we divide an odd number by 2, we know odd numbers are not perfectly divisible by 2. Okay. Yes. So yes, when we say odd numbers are not perfectly divisible by 2, it is very evident that it produces some remainder value, and that remainder value will always be equal to 1. Let's see some examples. Say for example, 395 is an odd number. So let's divide it by 2. So when we divide 2, 119, here 9, 18, 1, 5, 7, 14. The remainder obtained is 1. Let's see one more example. Suppose let's divide 1599. Let's divide by 2. Again, when we divide this, 7, 14, 19, 9, 18, 9, again the remainder obtained is 1. So when we divide an odd number by 2, it always leaves a remainder 1. Is it clear? Okay. Now let's take this expression. Now let's take this equation. Here the remainder value is equal to 1. here the remainder value is equal to 1, isn't it? Just now I have told you, when we divide an odd number, when we divide an odd number by 2, it leaves a remainder 1. Yes, so we can conclude x is a positive odd integer. X is a positive odd integer, and thus we have proved all positive odd integers are in the form 2q plus 1. Is it clear, guys? Thus we have proved all positive even integers are in the form 2q, and all positive odd integers are in the form 2q plus 1. Is it clear? Okay. So let me explain this. Once more. So in this question, you are asked to show that all the positive even integers are in the form 2q and all the positive odd integers are in the form 2q plus 1, where q is some whole number. Q is some whole number means the value of q can be 0, 1, 2, 3, 4, 5, etc. It goes on forever. Okay. Yes. So using Euclid's division lemma, you have to prove this statement. So you have to prove the given statement is right using Euclid's division lemma. Okay. So we all know the formula of, what is Euclid's division lemma formula? Yes, that is A is equal to, Euclid's division lemma formula is A is equal to BQ plus R, where the value of R is 0 less than or equal to R less than B. Okay. So the first four steps of all the questions of this type, are one and the same. Okay. So the first step is to assign some variable. To A. So here we assigned he assigned x to A. We assigned the variable x to A. That is, let A is equal to x. So here we can say x is the positive integer. That we are dividing. So x is the dividend. This is the first step. Okay. The second step is to find the divisor, or the number by which we have to divide the positive integer x. So in these types of questions, we have to choose the coefficient of the variable in the given expression as the divisor value. Is it clear? So in this question, the coefficient of the variable q is 2. So here the divisor is 2. Is it clear? Yes. Thus we got the dividend and divisor. Now we have to substitute these values. For A and B in the Euclid's division lemma formula, Euclid's division lemma formula, and we got x is equal to 2q plus r. Now we have to find the fourth step. Is we have to find all the possible forms of x. So how do we find all the possible forms of x? For that we have to find all the possible values of the remainder. Okay. So in this question, what are the possible values of remainder? Here in this question, the divisor is 2. That is, we are dividing the positive integer x by 2. So we all know the remainder value can either be 0 or values greater than 0 but less than the divisor. So since here the divisor is 2, only two values are possible for remainder, and they are 0 and 1. So since there are only two possible values of remainder, x can be in two forms. And the first form is x is equal to 2q plus 0, and the second form is x is equal to 2q plus 1. Okay. Yes. Now we all know even numbers are perfectly divisible by 2. Yes. So when a number is perfectly divisible by another number, yes, we know the remainder obtained will be 0, isn't it? Yes. So when we divide an even number by 2, the remainder obtained will be 0, because even numbers are perfectly divisible by 2. Okay. So now let's consider the first form. Now let's consider the first case, and in the first form, And in the first case, the remainder, when we divide the positive integer x by 2, the remainder obtained is 0. Okay, only even numbers are perfectly divisible by 2. Here the remainder obtained, here when we divide x by 2, the remainder obtained is 0. So we can conclude that x is perfectly divisible by 2. Yes, so I told you only even numbers are perfectly divisible by 2. So here we can conclude x is a positive even integer. Is it clear, guys? Similarly, only odd numbers leave a remainder 1. Only odd numbers leave a remainder 1 when divided by 2. Is it clear? Only odd numbers leave a remainder 1 when divided by 2. Here in the second form, the remainder value is equal to 1 when we divide x by 2. Is it clear? So we can conclude x is a positive odd integer. So thus we have proved all the positive even integers are in the form. All the positive even integers are in the form 2q, and all the positive odd integers are in the form 2q plus 1. Is it clear, guys? Yes. So let's discuss one more question. Let's discuss one more type 1 question here in this session. Yes. So here in this session, yes, I am discussing. So here in this session, I am discussing just 2 questions of type 1. Just 2 questions of type 1. Okay. After finishing this chapter, after finishing the chapter real numbers, yes, I'll discuss. After finishing the chapter real numbers, I'll discuss the questions asked in your previous year examinations. Previous year examinations means almost from 2010 to 2024. So in that session we'll discuss some more questions of type 1. Okay, yes. So let's discuss one more question and then we'll discuss how to find the HCF of 2 numbers using Euclid's division lemma. Okay. Use Euclid's division lemma to show that the square of any positive integer, is